Alright guys, welcome to part 2 of our two-dimensional collision problem, specifically an elastic collision problem. I had to cut the video in half because the first video was getting a little too long. So where we left off in the first video was we were pretty much discussing how the momentum in any collision is conserved. So the total momentum in our x and the total momentum in our y should stay the same before the collision and after the collision. So that's exactly what we're going to show when we solve for our momentum after the collision. So this is how we're going to approach it. Since we already solved for our initials, we're going to do our after collision, so our x component after the collision. And we have to take into consideration ball A and ball B. So we have the momentum of ball A finally, that means after the collision, and we know that's going to be the mass of ball A times the velocity that ball A has in the horizontal component after the collision. So if you look at it from face value, this was the direction, this yellow arrow was the direction that ball A shot off on. And I drew these two green arrows to show you the component vectors that this resultant orange line makes up. So what that basically means is that this orange arrow is made up by these two green arrows, one horizontal arrow and one vertical arrow. So we can use this information to solve for our horizontal velocity for ball A. And that's basically, we do mass of ball A times the velocity of ball A in the x direction. To find the velocity of ball A in the x direction, we have to understand that we have an angle here of 53 degrees, and we want to find the side that is adjacent to the angle. And we have the hypotenuse. So if we have adjacent and a hypotenuse, we know that the trig function we'll be using is cosine. So that means the cosine of 53 is going to be equal to adjacent, which is x, over our hypotenuse, which is 1. So basically, to solve for x, we just have to do the cosine of 53. And let's type that into our calculators. So the cosine of 53 will be roughly around 0.61. Okay, so our horizontal velocity component is going to be about 0.61 meters per second. So if we multiply that by our mass, so 0.61 times our mass, which is 0.2, we'll get a momentum of 0.122 kilogram meters per second. We'll do the same thing with ball B. Ball B after the collision will be the mass of ball B times the velocity of ball B in the x direction. Now, we see for ball B it's made up of a horizontal and a vertical component represented by the orange arrows. But the problem with ball B is that we don't have a defined angle that we can use any trig functions for. We don't know at what angle ball B shot off on. But that's no problem because, as we mentioned before, momentum is conserved. We see before the collision the total momentum in the horizontal component was 0.4 kilogram meters per second. Now we have in the final 0.122 kilogram meters per second taken up by ball A. Meaning, in order for this whole thing to equal 0.4, in order for momentum to be conserved, ball B must be equal to 0.4 minus 0.122. So let's do that. 0.4 minus 0.122 gives us about 0.278 kilogram meters per second. All right, so that's good. Let's move on to our y component. So we have to find the momentum of ball A in the y component. So that's the mass of ball A times the velocity of ball A in the y component. We see that the y component, the vertical component, is going to be this upwards looking green arrow. Because we know that that's going to be opposite over the hypotenuse, we can use the trig function sine of 53 equals x over 1. So essentially, we're just doing sine of 53, which is about 0.80 meters per second. So now we have to multiply the mass of ball A times the mass of ball B, so that's 0.2 times 0.8, and that's going to give us 0 0.16 kilogram meters per second. Same thing with ball B, except with ball B, we see that once again we don't have an angle, so we have to go back to our initial and see what our total velocity was for, or what our total momentum was for the y component. Here we see that the total momentum equals 0. And we know that momentum is conserved, so that means that our momentum after the collision has to be equal to 0 as well. We see that this ball A already contributes 0.16 kilogram meters per second. So in order for this finally to be 0 kilogram meters per second, ball B has to contribute negative 0.16 kilogram meters per second. So we pretty much did the bulk of the problem. But remember, the final thing that we need to solve for is we need to solve for the velocity of ball B. So how can we do that with the given information? Well, we can take two equations. This equation that has the velocity of ball B in the x component, and this information, which has the velocity of ball B in the y component. If we can solve for both our x component and our y component of ball B, we can solve for our final velocity, which is the resultant vector. So we have the first equation, mass of ball B times the velocity of ball B in the x direction equals 0.278. Now, can we solve for the velocity of ball B in the x direction with this equation? Absolutely. How is that? Well, we already know the mass of ball B. So we can divide both sides by the mass of ball B, which is 0.278, divided by the mass of ball B, which is 0.3, and we would get 0.93 meters per second in the x direction, in the horizontal direction. Same thing, we're going to use this equation now. The mass of ball B times the velocity of ball B in the y direction is equal to a negative 0.16 kilogram meters per second. If we divide both sides by the mass of ball B, we would get the velocity of ball B in the y direction to be negative 0.16 divided by 0.3, the mass of ball B. And that would be equal to negative 0.53 meters per second. And that makes a lot of sense because we know in our y direction it's going due south, so it has to be a negative velocity. So we can use these two pieces of information and solve for our resultant velocity. We can use that, okay, our horizontal is 0.93 and our vertical is negative 0.53. And to solve for our resultant, all we have to do is the Pythagorean theorem. So we do 0.93 squared plus negative 0.53 squared to give us some value. So 0.93 squared plus negative 0.53 squared. And that gives us about roughly 1.15. But that's not exactly what we want because this is giving us c squared if we go back to our Pythagorean theorem. We just want c. So we have to take the square root of both sides to get c to equal the square root of 1.15. And that's going to be 1.07 meters per second. That's going to be the velocity of ball B after the collision. But we're not done, because remember, velocity is a vector quantity. So that means that not only do we need magnitude, but we also need direction. The direction will be the angle at which this ball is going in. So we have to solve for theta. How do we solve for theta? Well, the main way we can solve for theta is we see that it's made up of these two components, opposite over adjacent. And we know the opposites and the adjacents. We know that the tangent of whatever theta is going to be, which is opposite over adjacent, will be 0.53 divided by 0.93. If we take the inverse tangent of 0.53 over 0.93, we will get theta. If we type this into our calculator, which is the inverse tan of 0.53 and 0.93, you'll get a theta to be about 30 degrees. Now, of course, you could have put a negative 0.53 and a 0.93 here and gotten a negative 30 degrees, and that's perfectly fine because this ball B is going below the x axis, below the horizontal. So you should, a negative degree would imply that you're going below the horizontal, but you could actually describe this to be the velocity of ball B to be 1.07 meters per second, 30 degrees below the horizontal. You could also describe it as negative 30 degrees. You could describe it 30 degrees south of east. There's a billion ways that you can give it direction, but you have to have some sort of directional observation in your answer so that this velocity will be a vector quantity. So this will be our final answer for the problem. I hope you enjoyed this video. I hope it gave you a lot of clarity on two-dimensional collisions that are elastic. I hope you tune in for more. Thank you for watching.